Today I'm going to maybe repeat a little bit just about the big background, but I will more focused on some what I think are unique problems in iron dust combustion, which are not studied in any other type of fuels or any type of combustion technologies. And I think these are something that we really need to focus on and develop new thoughts, new tools, and new technologies to solve them. Right. So just a little bit background. I think nowadays we are pretty clear that our energy crisis is not really due to the lack of renewable sources, but it's really because these sources are intermittent and also geographically scattered. But the demand for energy is continuous, right? We cannot turn off our heat during the winter, although the solar energy is more abundant during the summertime. And also, as you can see on the right figure here, there are a lot of wind energies. Wind power can be harnessed on the seas, on these offshore places, but electricity is needed everywhere, even far inland. So supply and the demand are not really equal to each other in time and space. So to solve our nowadays energy crisis, the real question is how to efficiently store and transport renewable energy, right? And what we are looking for now is the solution of good energy carriers or energy storage, right? And then in our conventional terminology in combustion, we call these things the fuels, right? So what are the options? Let's look at the periodic table. We know that we do not want carbon, right? We want to replace carbon, replace fossil fuels to reduce the CO2 emission. So let's cross carbon out in the table. And also we do not want those things cannot be easily oxidized. Either they are oxidizers themselves or they just react too slow in air or with water. Also, we do not want these heavy elements because they are heavy, their energy density will be quite low, right? We do not want these rare metal or rare elements because they are very expensive. Also, we do not want anything toxic. Another thing I would like to cross out is these metals which are too reactive. Like you can very hardly control their reaction, like sodium, potassium, and so on, right? Then if we look at this table again, there are not many other not many options left. Nowadays, there's a lot of attention paid to these two elements, hydrogen and lithium, right? But there are some drawbacks with this type of these elements using as energy carriers. Well, one thing is the low energy density. So in this small cartoon, it shows that to contain the same amount of chemical energy, you need this one tank of diesel. But if you use compressed or liquefied hydrogen, you need 5 times more volume to contain that. And if you talk about lithium-ion battery, because it has to carry both anode, cathode, and the electrolyte materials in there, and only the lithium-ion can transport energy, then the energy density is much lower. So you need that many tanks or volumes of lithium-ion battery to carry the same amount of energy. And also, hydrogen has always this fire and the explosion hazard. And also nowadays, people are talking about this thermal runaway and the fire hazard with the lithium-ion battery as well. Another drawback with these batteries is it has a kind of a slow discharge rate or loss of energy rate, about 3% per month. This is okay for your passenger car or your electronic devices. It's not that fast. But if you use this type of battery for seasonal storage of energy, this percentage accumulates and the loss will become significant. So what we are talking about now is this metal-enabled cycle of renewable energy, or MECR. That's the idea is not mine. It has been first proposed, I think, back in 2005 by a professor in the US called his last name is Beach. I forgot his first name, but was the real first paper proposed this idea. And then was in the mid 2010s, Jeff Thurston and some other colleagues at McGill reproposed this, and then my colleague Professor Philip de Hooy imported this to the Netherlands, and now he's perhaps the most active researcher to upscale this idea to a global or to an industrial scale. So the idea is quite simple. You burn some metal powders. Right now, the most promising candidate is iron. You burn iron dust. It releases heat, which can be used for power generation or just use as heat itself. It has no CO2 or any other polluting emission. And these particles can be recycled after the combustion. And this recycled iron oxide can be transported to somewhere you can get easy access to renewable energy. And this renewable energy can be used either to produce hydrogen or directly reduce the iron oxide through some electrochemical processes. Then you can regenerate your iron powder. Right, this iron powder can be again transported to somewhere you need to consume the energy or to generate power. So in such a way, renewable energy can be transported over long distance and also stored over long time. So I would like to bring your attention to this feature or advantage of iron. Iron has this potential to be 100% recycled after combustion. This is because it has very high boiling point. And during the combustion process, the temperature of this droplet or particle won't exceed its boiling point. So it won't evaporate very violently. And throughout the entire combustion, it stays in condensed phase. First in solid phase and later in liquid phase, but it never completely evaporates into gas phase. And this is quite different from some other metals like aluminum, magnesium, which have a relatively low boiling point so that their combustion is volatile, wherein you evaporate the fuel first and then most of the energy release happens in the gas phase. And because of this unique feature of iron combustion, it gives out some very unique characteristics or very unique problems that we need to solve with iron dust combustion. One thing is this heterogeneous oxidation process. Because the particle remains in solid and liquid phase throughout its entire combustion, then there's always an interaction between the gas phase oxidizer and the solid phase fuel, right? And also because this non-volatile combustion, the energy release is always first concentrated in the near vicinity of the particle. So that makes the energy release over space highly discrete, right? As opposed to a more homogeneous or volatile fuel that's in gas phase, the energy release is more homogeneous and spatially uniform. So let's look into these unique features, because the real physics or the real new problem that we need to tackle that we cannot use our existing knowledge from combustion to explain are related to these unique features, right? Okay, let's look at the first one. So iron particles are stored in solid phase. So to start combustion, first of all, the reaction must happen in solid phase, right? And to understand the solid phase oxidation mechanism really allows us to understand the ignition process of iron particle. So this, we can find some information from this 1950s metallurgy study. They studied how this iron oxide scales build up on a sample of iron. you can see that there are multiple layers. There's a very thin layer of hematite or Fe2O3 on top, and then another slightly thicker layer of magnetite Fe3O4 underneath. And then the majority of this oxide scale or oxide layer is the woostite, FeO, right on top of the iron sample itself. So this sample is opposed to air and kept at a constant temperature. So people can measure the thickness of this different layers over time, and from there they can get some kinetics. And the mechanism driving this oxidation is the following. You have multiple layers, and then in the first layer, you have both bidirectional diffusion between iron ions and oxygen ions and iron ions. And in the other layers, oxygen ions cannot really easily squeeze through it because oxygen ions are big, and then through this lattice, its mobility is very low. It's mostly depending on the iron ion to diffuse outward and then meet up with the oxygen stored in the lattice to form these layers. So this overall oxidation process is mainly limited by the rate of Fe ion diffusion through these two thicker layers. And FeO layer is definitely thicker, so this layer, Fe iron ion diffusion through this layer is the rate limiting step. And then we can just take this idea and then wrap these layers around to build our single particle model for solid phase oxidation, and use this to study the ignition characteristics of iron particle. And we use just a simple heat and mass balance equations. We solve that. We can have the result of particle temperature as a function of time, but for different gas temperatures. So you can see for some relatively low, where the gas temperature is below a certain value, the particle is being heated up a little bit, and then cools down, and then eventually become the same temperature with the gas. But if this gas temperature is greater than some critical value, you see this significant increase in temperature of the particle, and this is known as the thermal runaway, which means the heat release rate of the particle becomes greater than the heat loss rate into the surrounding. And if this happens, we know the particle is ignited, and the minimum gas temperature Tg that can trigger this thermal runaway is determined as the ignition temperature. And we did some parametric study. This is ignition temperature determined using this model as a function of a particle size. And different lines represent different conditions, like different initial oxide layer thickness. And if the oxide layer thickness are very thin, you see there's not much difference as you go to a very large particle size. And also the radiation effect is not very significant, because this thinner lines are without radiation, and the thicker lines are with radiation. The difference is quite small at this lower around the ignition temperature. So for this large enough particles, this ignition temperature is estimated by this model to be somewhere between 1080 to 1100 K, right? And right now, the only experimental value we can compare with is not for iron particles, but for iron foils, or a small piece of iron holded by some supporter. And they determine this ignition temperature in a similar definition as we use here. And they can show that this temperature are not too far away. I think is less than 10% different. But since they are holding these samples with some solid frames, then they also experience some conductive heat transfer, heat loss. and those can increase the required ignition temperature. But the two main assumption we made in this kind of a model is from this metallurgy study, and this gives us some unique features that this ignition temperature plateaus as the size of the particle keeps increase for larger and larger particle size, and also this ignition temperature is independent of oxygen concentration in the gas. This sounds counterintuitive, but the reason is that this very top layer of Fe2O3 can adapt its own growth rate to the oxygen concentration in the gas. But once this layer is formed, then the interface between these layers are just at the equilibrium, and the internal diffusion is completely driven by the gradient between these layers and the thickness of these layers. So gas phase, gas phase concentration or the collision frequency of the gas phase molecules is not really the rate limiting factor, right? It can become a rate limiting factor if the oxygen concentration is really low. According to the literature, it has to be lower than 10 to the minus 4 atmospheric pressure in terms of partial pressure to become rate limiting. That means for any normal like air to 100% oxygen, the collision rate of this O2 molecules, and they are way faster than the internal diffusion rate, so they do not become a depending factor. But this is all based on this assumption using this model. I'm not saying this is 100% correct, because there's no experimental measurement of particle ignition temperature yet, and this experimental verification is required. And once the particle ignites, it can increase to its melting point, and then eventually the full combustion process will happen in liquid phase, between the liquid phase particle and the gas, right? And what are these, what could be the possible limiting factors that controls the liquid phase oxidation? One thing is still this external transport of oxygen molecule from the bulk gas to the surface of the particle. The other thing is the surface chemisorption, like how much of this oxygen molecule reach the particle surface can be absorbed as ions into the particle. And also the internal transport of Fe and O ions could also be a rate limiting factor. And another thing which is actually not very likely rate controlling is the reaction rate between your Fe and O ions. So why I'm saying this is not very likely the case, because at this very high temperature, once this oxygen is already dissociated into the particle as ions, they can react with the iron atom very quickly. There's almost no activation energy required for this reaction to happen. So the reaction rate itself might not be the rate limiting factor because it's very rapid. So the question is, which one of these three, external transport, surface absorption, internal transport, or an interplay among them is the real rate limiting mechanism? So let's try to answer this by some study. We'll go through some study. It's more like finding different pieces of the puzzle, and I will just, by the end of this part of the talk, I will show you how far we have gone at the moment and what are the remaining unknowns. Right, to start this journey, then first we need some experimental anchor point, right? We need some time scales, some first-hand experimental input. Otherwise, we're just guessing different things and making different hypotheses without really having any physical touch on the reality. So the two set of experimental data we are I'm going to talk about are both from a single particle combustion experiments. The first one is obtained by a former PhD student at TUE, Dao Mi, and his colleagues. He used this laser ignited particle reaction system. So this is like a top view of his of this burner, and the particle is emitted from this center point. It's coming out of the page, and then it will be heated by a laser. Laser can ignite the particle, and then the particle's trajectory and its combustion process will be recorded by the cameras, and the temperature can then be measured through this two-color pyrometry system. And another system studying iron particle combustion is in this drop tube. This is done in the US by the Northeastern University in Boston. They have this drop tube. You can have this hot gas at the temperature of 1350 K, and they studied different oxygen concentrations inside the tube from air to 50% and 100% oxygen. So they used the three-color pyrometry obtained from the top of this tube, and the particle is falling down in the middle. And this is not the right illustration, because this is like a whole bunch of particles burning at the same time. But to obtain the single particle history of temperature, you need to have this single particle burning in the entire tube. So let's look at these results. The most important result that we can use to compare with our model and the hypothesis are this temperature history of the single particle burning in different conditions. So this is the one that Dao Guanning and his colleagues obtained. This curve right here is the temperature, and this is for a particle size around 54 micron, and this is in air. And the surrounding gas temperature is just at the room temperature, so it's considered as a cold surrounding. And you can see the peak temperature can go up around maybe 2400, below 2500. And these are some results obtained from this drop tube experiments. And these authors performed the two set of particle sizes, although not very far apart. This is from 38 to 45 micron, and this is 45 to 53 micron. And they did this in three different oxygen concentrations. The top one is in air, the middle one is in 50% oxygen, and the bottom ones are in 100% oxygens. Right. And we are having our, not only, TUE and McGill, but also some other universities participated in this, what I call early campaign of FE particle modeling. But I'm going to only review a few ones that I'm more familiar with to let you know what we learned from this early stage of modeling. So in this early stage modeling, we did not include all the possible physics, because we want to start with something simple and then to see if this simple model can capture the most essential physics. So we made the following assumptions. We assume that the internal transport is very fast, is infinitely fast. So that we just, eliminate that as a rate limiting factor. And we assume that inside this liquid particle, FeO is the only product. And once all the iron is converted to FeO, that means the molar ratio of oxygen inside the particle is 0.5. We just assume that the reaction is over. The particle just cools down inertly. And also on the particle surface, we assume a 100% absorption of oxygen. As long as the particle, the molecule of oxygen can reach the particle surface, it can be absorbed into the particle. And the heat and mass transfer in the boundary layer around the particle we assume they are in the continuum regime. And in the model to calculate this transfer rates over the boundary layer, we use the continuum model. So this is what we got. These are two independently developed model. On the left, this is work developed by my colleague Leon Theis and his colleagues. He used a boundary layer resolved model. So basically, it's a 2D axisymmetric model. You resolve the gas boundary around the particle. It's not a single 0D particle model. And then he shown that his result, this solid line, matches with Dao Guanning's experimental result, the laser ignited cold environment result pretty well. I mean, overall, the trend is pretty close. And also the peak temperature are pretty much well agree with each other. And a student that I supervised back at the McGill University, Aki Fujinawa, he also did this job using just a 0D model without all this detailed or more accurate resolution of the boundary layer dynamics. His results maybe it's not as good as Leon Theis' result, but it's overall okay. Like the separation between the peak temperature of the experiments and his result is, I think, somewhere, you know, just 100 degree, something like that. And the overall time scale reaching the peak point is also quite close. But from both of these results, there are something that we need to remark. Some obviously disagreement with the experimental data. One thing is the heat up process seems faster than the experimentally recorded data, although the experimental data also have some error bar, some uncertainties there. And the other thing is since we stop the reaction after everything is converted to FeO, the cool down seems to be much faster than the experimental data, right? And this gives us some hints that the FeO might not be the final destination. There must be some further oxidations up on the cooling of the particle, right? It gives you higher oxidized product, and this hint or this hypothesis that we reached after comparing our experimental result, our model result with the experimental result, is actually supported by some other experimental evidence. So these are some particles burned from one of our burners, and these were given to some collaborators. She was at the Max Planck Institute for Iron Research in Germany, and they can manage to cut the particle and look at the cross section of these particles, and using this backstack scattering electrons to look at what are the different crystalline structures of different parts of the particle. And this allows us to know where the particle is magnetite, like Fe3O4, where is hematite, and where is other things like woostite or iron itself. So these completely burned particles, they show that there's no iron left at all. That means it's definitely completely oxidized. And you can see that most of the particle is converted to Fe3O4. And maybe in this case, there is a tiny bit of FeO left in the middle. And near the surface, you also have some even further oxidized product, Fe2O3. But we know that Fe2O3 can only be stable in solid phase. That means before the particle gets solidified, the whole particle is nearly converted to Fe3O4. So this actually supports our hypothesis that we shouldn't stop the reaction at FeO in our model, right? If you stop there, then that contradicts with the experimental evidence. And if we look at this phase diagram, this in the x-axis is the molar ratio of oxygen, and in the y-axis is the temperature. You can see there are different phases this mixture between oxygen and the iron can go. And in the middle, you have this two liquid region where your liquid iron and the liquid oxide, we approximately understand that as the liquid FeO are immiscible, so they are two separate phases, and we think that in the early part of the combustion, you just absorb more and more oxygen, so that the particle keeps oxidizing in this phase, and the temperature keeps increasing up to a certain point. And then later, beyond this point, particle can get further oxidized. So the FeO stoichiometry is here, right? It's nearly this boundary of this phase diagram, and the particle can be further oxidized until some point it reached this line. This line is the boundary or the limit of oxygen saturation into the oxygen solution into the particle. So if you reach this line, that means that there's no more oxygen can be dissolved into the particle, and it has to cool down because there's no way to absorb more oxygen and no way to generate heat through the oxidation. But if you follow this boundary, this saturation boundary, and you can see that it's actually beyond the stoichiometry of the spinel or the magnetite. So that means if you get to this point in the liquid phase and get solidified, the particle actually contains more oxygen than it is required to form Fe3O4. And what happens next is the particle need to expel this oxygen, right? And this is what we understood that why we are seeing these big bubbles, or some of the particle has this opening on its surface. So upon the cooling, upon the resolidification process, some excess of oxygen is expelled out of the particle. Okay, let's go back to our model. We try to also compare our model prediction with the drop tube experimental data for higher oxygen concentrations. So this is the one for 50%, and this is the one for 100%. Unfortunately, both of them fail, right? We cannot capture this experimental data. So there is still some debate. Maybe these experimental data are biased or somehow is influenced by the formation of nanoparticles. So you didn't really capture a higher temperature of the particle themselves. They are, surrounded by some nanoparticle due to the evaporation of iron. But this is still uncertain. We are waiting for some of our colleagues to provide us further confirmation on this. But the model doesn't seem correct as you go up to a higher, nearly 100% oxygen, because the particle definitely didn't fully evaporated. That means the particle didn't reach its boiling point in any of these experiments. And if your model prediction tells the particle would go up to the boiling point, that is not correct. So that makes us to think what are the missing physics and how we can add them into the model. And we can take a break here. That I think this is why I like studying iron combustion, because we can find a lot of contradictions. So this was once remarked by Niels Bohr that particle work lacks a contradiction at his time, and he thinks until one contradiction is discovered, there will be no progress. And iron combustion, I guess we will have a lot of progress, because right now we have a lot of contradictions. Anyway, let's think about what are the missing physics, and coming back to this picture again, right? Before we have external transport, but modeled as a continuum transport. But we know that at this very high temperature, the molecular mean free path of the gas can become larger. So the whole particle size may become more comparable to the mean free path, and you may end up being in the particle may end up being in a Combustion transition regime or free molecular regime of heat and mass transfer. That's number one. Number two is the surface chemisorption. Before we assume that all the gas molecules can be absorbed into the particle upon their collision with the particle surface, but there could be some accommodation limits, like maybe some of the oxygen molecule can be just bounced back without being dissolved into the particle. And the reaction, although they are very fast, but before we only assume the product is FeO, and after FeO is formed, we stop the reaction, and this is not supported by the material characterization evidence. So we want to have some further oxidation beyond FeO. And also, we assume that the internal transport is very fast, but maybe this is also not true, right? So at some point, we have to also consider a finite internal transport rate. But let's not put everything together, because to really include this finite transport rate inside the particle, you need a particle resolved model. You cannot do this analysis with a 0D point particle model, right? So let's build a model only taking these three ingredients whilst keep the assumption of very fast internal transport. Let's see how much improvement we made to the model. And to consider Combustion transition regime of heat and mass transfer, we take this model, this paradigm that has been used in the literature, which is the two-layer model. In the inner layer, or in this so-called Combustion layer, the heat and the mass transfer is governed by the free molecular regime mechanism. And outside this layer, we still apply the continuum heat and mass transfer model. And the thickness of this Combustion layer is equal to the gas phase molecular mean free path, which can be calculated as a function of the boundary layer temperature. And as I said, inside this layer, inside this Combustion layer, the mass and the heat transfer rate are calculated using the free molecular regime's heat and mass transfer model. And this looks different from the continuous heat mass transfer model. And you can remark there are two important parameters here, which are the mass accommodation coefficient and the thermal accommodation coefficient. The mass accommodation coefficient measures how much of the molecules can be absorbed into the how many of this molecule can be absorbed into the particle divided by the total number of molecules colliding the particle. And the thermal accommodation coefficient measures the maximum energy that can be exchanged by a molecule reflected from the particle surface to the actual energy exchanged between the molecule and the particle surface, right? So you can see this bracket here. This means it is an ensemble average that you need to, measure this over a big number of particles or molecules to get this result, right? But these values for liquid iron and iron oxide surface with oxygen and the nitrogen molecules are not available in the literature. So we decided to use molecular dynamics simulations to do this. And this work is mainly done by our PhD student, Leon Theis, collaborating with the PhD student Stratos in the Empirical College of London. And they performed MD simulations to measure thermal and mass accommodation coefficient for iron surface and also iron oxygen mixture surfaces. And the methodology is used here is called the molecular beam simulations. And the idea is you shoot one single molecule towards this surface, and then you can measure, whether it is absorbed into the surface and what is the energy exchanged before and after the collision, right? And after you repeat this simulation many times with the different incident velocities of the molecules according to a certain Maxwell-Boltzmann distribution, you can obtain this ensemble statistical average result for MAC and TAC, right? So here are some results. On top here is the result of TAC for both iron surface against some nitrogen molecules, and also Fe and O mixture surface with oxygen molecules. And you can see that this here is a function of this TAC as is the TAC of for nitrogen as a function of temperature. It doesn't seem to vary that much between the value of 0.1 and 0.2 over the liquid phase temperature range. And here is the TAC for this system as a function of the oxidation degree or the oxygen molar fraction in the mixture. So you can see there is it is almost constant for a while, nearly a unity, nearly 100% absorption, until you reach ZO equals to 0.5, which is the stoichiometry of FeO. And if you look at the result of mass accommodation coefficient as a function of the oxidation degree, this trend is more interesting, I guess. You can see that the mass accommodation coefficient decreases. That means that the more oxygen dissolved into your liquid particle, the less likely you can absorb more oxygen on the surface, which makes sense. And also you can see that once the ZO is beyond 0.5, this value drops down to a very small value. It's not exactly zero. There are some finite rates. You can still intake some oxygen into the particle, but the value is much smaller than what is for lower ZO values. And FeO stoichiometry is actually here. It's at 0.5. That means after you oxidized up to FeO stoichiometry, the further intake of this of oxygen into the particle will become harder and very likely become a rate limiting factor, right? Okay, so we take this MD simulation informed accommodation coefficients, and we can perform some 0D single particle combustion modeling and to get some results. And here you can see we considered the effect of Knudsen transition regime of heat and mass transfer, because we are using this two-layer model, and some surface chemissorption limit by considering the mass accommodation coefficient below unity, and also the oxidation can happen beyond the stoichiometry of FeO. But we are still assuming infinitely fast internal transport of FeO and of Fe and O atoms. And this is some results. The solid line is again the modeling results, and this small dotted line is the experimental result with the arrow bar, which is the shaded region. You can see again for this relatively low oxygen concentration, the matches very well, and we do not see that sharp pointy peak temperature anymore. You have a more smooth transition from temperature increase to temperature decrease, and the temperature decreasing part or the cooling part seems to match the experimental result better. You have because in this case we do not have a inert cooling anymore. We have this further oxidation towards a higher oxidized product, and also the heating seems to matching the experimental result also better. because you have these limitations to slow down the reaction rate, right? But the problem is, if we look at what happens at the higher oxygen concentration or higher environment temperature that are obtained experimentally in this drop tube setup, the match is not as good as for this cold environment, low oxygen concentration. So for this 21% or air at this higher temperature, the overall trend is okay. It's not too bad, the match, but you can see the peak temperature also somehow overshoot over the experimental result. And this overshoot becomes larger and larger as you go to higher oxygen concentrations. And again, the experimental result doesn't show a very significant peak temperature increase as you go from 50 to 100% oxygen in the gas phase. So this leads us to our final, or I hope it's final, but maybe there are also other unknowns. We were wondering, is this internal transport really the last missing piece of the puzzle, right? Anyway, so there are some preliminary results to look into this direction. But as I said, if we want to resolve what happens internally inside the particle, you need a particle resolved model, and also you need some diffusion coefficients. But our student managed to get this diffusion coefficients of Fe and O within this high temperature liquid mixture using MD simulations, and this allows him to proceed with some particle resolved model. And this is just some very preliminary result that he obtained. You can see that inside the particle, you can even have some non-uniform distribution of a velocity, because the particle, for example, in this drop tube, there is a slip velocity between the particle and the gas. So the gas can give this momentum to the liquid inside the particle, and this liquid can swirl and create this non-uniform velocity field within the particle. And this is only with about 7 milliseconds after you supply oxygen to the particle, and you can see a clear gradient, spatial gradient inside the particle. So that means that the transport of oxygen inside the particle is not as fast as we assumed before, right? This internal transport might happen over a time scale that is comparable to the entire combustion process, to the other transport processes. So I think this is very likely the right direction that we need to look into. But you may get frustrated that we just keep adding more and more complex physics. And this is the code that my supervisor, my PhD supervisor, always made. Any darn fool can make something complex. It takes a genius to make something simple, right? Because if we keep adding the dimensions, keep adding the physics into the single particle model, nobody can use that for any CFD computations, right? But also, nowadays, I think this become a cliche quotation that all the scientists quote: everything must be made as simple as possible, but not one bit simpler. Okay, I will go relatively fast with the other feature because it is even more complex and we have even less certain answer to it, but I think it's still very interesting. As I said, since iron particle has very non-volatile combustion, the energy release is within the very close vicinity of the particle, and this will make the overall energy release over space highly non-uniform or highly discrete. So to understand this phenomena, we can look at this ratio between two key timescales. One is the reaction time. T reaction is the time over which an iron particle releases its energy, and the other is the characteristic time scale for the heat to diffuse from one particle to its neighbor, right? And if this parameter is very large, much larger than 1, that means the reaction time is much longer than the interparticle diffusion time. Then after a particle releases energy, it has enough time for the heat to smear out and become smooth over the space. So the resulting flame structure using like a toy model, it's not really an iron flame model. It's a very simplified theoretical model that we developed a few years ago. Not we developed, but we used that to study this problem a few years ago. At this very large chi parameter regime, you see a flame that is continuous and very similar to what we have seen as a laminar flame in gaseous flames. But if this chi parameter is much smaller than 1, that means your reaction time is much smaller than interparticle diffusion time. And after each particle releases heat, it takes time for the heat from one particle to reach its neighbor. And then the resulting flame is totally different. It gives you this highly non-planar flame front and with all these finer details between the particles. So these are only theoretical pictures. Like what really happens in real world iron dust flames? Is it something in between or something even more complex? Unfortunately, I think the picture would be even more complex because for any realistic burners, you must burn your iron dust in a turbulent flow, and the turbulence itself can can inhomogenize your space, your temperature and the flow field, right? And this highly discrete energy release particles are carried by this turbulent flow, and the picture is even more complicated. So to understand this complexity, we can do this thought experiments. Nowadays, all these turbulent iron dust burner developers are competing, commercially. So they do not want to release any measurement or dimensions to the scientific community. That is understandable. So I compromise with that, and I publish the work using a coal turbulent burner from Cambridge, and just assume that an experimental or small scale iron dust burner has some similar operation conditions or similar turbulent characteristics. And these are some typical burner inner tube diameter and also the mean velocity of the injected flow, which give a rise to a Reynolds number around this value, 7,500. And this will give you integral length scale and the chromograph length scale, which were both measured by PIV in this published work. You can see the integral length of this turbulence is somewhere between 0.5 to 1 centimeter, and the chromograph length scale is around 100 microns or 0.1 millimeter. So, but we need to understand how this turbulence interact with iron particles. So we also need to look into some characteristic length scales of iron dust. So iron particle size in our typical applications would be around 50 microns or on that order of magnitude. And if you are talking about burning them in air with an equivalence ratio of FeO, for FeO equals to 1, then you end up having a mean particle spacing around this value, somewhere below 1 millimeter. And if you compare these different length scales of particles and the turbulence, we can, just get a few, we have a few remarks from this dimensional analysis. The first one is the particle size is actually smaller than the chromograph length scale of the turbulence. So viscous drag on these particles tends to dissipate the turbulent kinetic energy. That's number one. Number two is this particle spacing is actually between your chromograph length scale and the integral length scale of the turbulence. So this is interesting. That means your particle itself intends to dissipate the TKE, but the discrete energy released from these particles tends to enhance or to produce more turbulence kinetic energy, because the spacing between the particles are, in this intermediate or energy producing length scale range. And the last remark, I think is even more interesting and more unique to iron combustion, is that the particle Stokes number can range, depending on you're talking about the Kolmogorov length scale or integral length scale, but this Stokes numbers can range from 0.01 up to 10, right? So Stokes number is the measure of how well the particle can be entrained by the flow. Right, the smaller Stokes number is, that means the smaller inertia the particle have, then the particle can be more easily entrained by the flow. And the larger Stokes number, the larger inertia of the particle comparing to the flow. And in that case, the particle more behaves like a cannonball. It doesn't really follow the gas, right? But what is interesting is in this intermediate regime, when this Stokes number is around unity, then you will see some interesting phenomena, which is known as the preferential concentration or clustering of particles. And why this is unique or uniquely important for iron combustion, you can see here, this is what I said, they have a different pictures, different simulation pictures, not for iron, but just for some inert particles. When your Stokes number is around unity, you can see the particles are concentrated at some thin regions rather than uniformly distributed over the space. And if your Stokes number is much smaller than 1, it follows the flow field, right? And if Stokes number is much greater than 1, they do not, the particles do not follow the flow field, but they do not concentrate on these preferential regions, because they just don't really care about the flow. They don't sense that their inertia are too large to be easily entrained by the gas flow, right? So why this is important and uniquely important for iron, I think there are 2 reasons. One is that iron has very high density comparing to other solid fuels like a coal or even aluminum or sprays of liquid fuels. That's number one. They will give iron high inertia. The second one is, again, this unique feature that iron combustion is non-volatile. For those volatile fuels, although they can have some interesting or intermediate Stokes number at the beginning, but they will evaporate. They will become a gas phase, right? The combustion happens in gas phase, but iron combustion is non-volatile. They remain in condensed phase throughout the entire combustion. So they remain at this high Stokes number particles throughout the entire energy produce process. So we really need to care about this phenomena. And what could be the effects of iron dust combustion, the effects of a preferential concentration on iron combustion? Is one thing is that this can significantly change the local particle number density. So particle can collide in this very narrow and highly concentrated regions, although the overall average volume fraction of iron is still quite low. In typical applications, it's below 10 to the -4, right? It is actually very low, but if you have this preferential concentration in some regions, the particle can collide and then form agglomerations. And then the second one is you can change the local equivalence ratio. So maybe in a certain region, where the particle are highly concentrated, you can have either local quenching or not complete oxidation up to Fe3O4, right? And here I will go fast. I know I'm running over time. So we are now starting doing some gas phase or carrier phase DNS to resolve the particle interaction with a turbulent flow. And in this case, it's actually not turbulent yet, because to resolve higher Reynolds number, it requires a higher computational cost. But you can see even for this very low Reynolds number flow, the particle energy release can trigger some turbulence or turbulent-like flows. That actually supports our hypothesis before, that the particle spacing, they can happen in a region that this interparticle gradient can produce kinetic energy of turbulence, right? And the further studies or more extensive results from this simulation will be presented later this year at different conferences. Okay, so since I talked about a lot of things that are uncertain, I don't think we should make any certain or concrete conclusion. So rather than having a conclusion slide, I just list some outstanding problems that I would like to invite all the listeners to this talk or the future viewers on YouTube to join our collaboration and our effort to tackle these problems. So first of all, as I said, for the solid phase iron particle ignition, we do have some theoretical model, but that theoretical model is based on some metallurgy kinetics. We do not have any direct measurement of the critical temperature required for solid iron particles to ignite. And this experimental proof or verification is required. And the second is about the heat release rate. I talked all about these fundamentals. Eventually, for engineering, for technology development, people just want to know, like, if you burn this much iron particles, how many watts or how many kilowatts produce energy, right? But to really know this, we cannot ignore all these fundamental unknowns into the heterogeneous oxidation mechanism, into this highly non-uniform combustion, even further complicated by the turbulent preferential concentration of the particles. And another one that I didn't have time to include here is the heat transfer via radiation to the surrounding and from particle to particles. And the last one would be, there are also some side products from iron combustion. Because you are burning them in air at high enough temperature, you definitely have some NOx production. So we want to understand how does this liquid iron particle surfaces interact with NOx formation, whether you reduce NOx formation or further enhance it, right? And also the liquid iron particle, where its oxide product can evaporate to a certain degree, and this evaporated gas phase iron can further oxidize and produce oxide nanoparticles. And these nanoparticles are not, first of all, is harmful for people's lungs, so you don't want to inhale them. You need to filter them and then not release them to human. And also this can be a loss in the iron mass within this energy cycle. So definitely we want to explore different ways to gauge how much oxide nanoparticles produced from iron combustion and how to reduce them, right? And here I would like to thank you all for your attentions. And I know this is very long and maybe a little confusing talk, because there are too many uncertainties, and I would like you to ask the questions, and some of the questions I can answer now, and hopefully some questions will be answered in the future. Thank you.